So this lesson is about figuring out the shape of molecules. And really in this lesson we're just figuring out the shape of really simple molecules. In high school chemistry we don't get into the more complex things. We're taking some previous knowledge about orbital notation, some previous knowledge about electron dot notation, and using that to figure out how bonds and lone pair electrons arrange themselves around a single atom. So the homework was to find the three-dimensional shape for a combination of phosphorus and fluorine in two different ways, and one was to use orbital notation. Anytime you're doing covalent bonding, and I'm sure in physical science you were taught that when you put together two nonmetals like phosphorus and fluorine, you're doing covalent bonding. Anytime you do covalent bonding, I taught you yesterday, you have to do hybridization. So we have to hybridize the valence level of both the phosphorus and the three fluorines we're going to combine together. Now the reason we know that we're going to put one phosphorus and three fluorines together is that fluorine has only one empty slot available here for electrons, and phosphorus has three. So we can share three with phosphorus, and fluorine can only share one, that is one electron and three electrons. And so that's how we know we're going to get a 1-to-3 ratio. So to hybridize then, using orbital notation, any way to designate that then, we're going to combine 3s and 3p. The lower energy level electrons, lower primary energy level electrons, do not change their structure, so that's going to remain exactly as we show it here. We're going to combine 3s and 3p, so that's going to give us 1, 2, 3, 4 orbitals all combined together, and we're going to call this an S, and since we're going to use all three of these orbitals, an SPPP, or better, it's better to say SP cubed, or SP3. Okay? And it's in the third primary level, so we'll use a coefficient 3 to show that. I have 1, 2, 3, 4, 5 electrons. I'll put them one in each of the boxes. When I finish putting one in each box, I can pair up one more to get to the 5 electrons. Okay? And that's the way that we would hybridize the P. We're going to hybridize the valence level. That's the highest primary energy level, designated by this coefficient number here. And so we're going to put together the 2s and the 2p, make 4 orbitals. Because I'm starting with 4 orbitals, I'm going to end up with 4 orbitals. 1, 2, 3, 4. I need 1, 2, 3, 4, 5, 6, 7 electrons. 1, 2, 3, 4, 5, 6, 7. You can put one in each box and go back and pair them up. And we need 3 of these fluorines. So this electron can share, we can share those two orbitals can be combined together. These two electrons can be combined together. The orbitals can be combined together, and you share the electrons in the same orbital. Okay? And when you share an orbital, you create what's called a bond. A covalent bond is a shared orbital. Okay? I want you to remember that. That's very important. All right? A covalent bond is a shared orbital. That makes sense? Got that? All right. Then if I have a phosphorus and 3 fluorines, the phosphorus has a pair of electrons here that are uncombined, and those are actually still remaining around the phosphorus. So the central phosphorus is going to have a pair of electrons that are uncombined, and then you're going to combine or share 3 electrons with 3 different fluorines. Okay? And they arrange themselves this way so that those pairs of electrons can be as far apart as they can possibly be, and it has to be arranged this way because once you create a bond, you're actually pulling the electrons from that double balloon shape we made for p orbitals into kind of a single balloon shape where we're trapping the electrons on this side of the phosphorus. So the electrons don't really spend much time on the other side where the other side of that p orbital used to be. It's all like pulled over to one side. The dotted line can be on this, the dotted line and triangle can be on this side. In fact, the dotted line and triangle can be at the top. Okay? The lone pair can be on any one of the four arms. Okay? For this tetrahedral shape, where you put them really doesn't matter. okay, because the angles are all the same. They're all 109.5 degrees apart, okay? Now, if we're going to use Lewis dots to figure all this out, then we see that phosphorus has 5 valence electrons. 1, 2, 3, 4. Put one on each of the 4 sides and pair up as needed. And so that would be the electron dot formula for phosphorus. Then the electron dot formula for fluorine would be this. We started out with 7 electrons, 1, 2, 3, 4, 5, 6, 7. So we put one on each of the 4 sides, pair up as needed, leaving us with 1 unpaired electron. And really, I'm not doing it the way I taught you to do it. 1, 2, 3, 4, one on each of the 4 sides, and pair up as needed. Okay? So those are electron dot formulas. You need to know that's what that name is. It's an electron dot formula for these 4 atoms. Okay? And we're going to change this set of electron dot formulas into a sharing arrangement by showing how we can share the electrons. All right? Now, from now on, we're only going to be doing it this way. We're not going to be doing all this other stuff. But it's important that you understand this doesn't show you how we're sharing an orbital. This does. And it's important that you understand what we're doing is not just sharing electrons, but sharing orbitals. And the new thing I told you today is that when you share an orbital, you create what's called a covalent bond. When you share an orbital, you create what's called a covalent bond. Got that? That's important that you know that. All right, so that would be our sharing arrangement then. From that, then we can do a Lewis dot formula. And the way that I explain this is that you take these 2 dots and just kind of squeeze them in between the 2 element symbols. Okay, and notice they're over and under, if your elements are right to left, and side by side if your elements are above and below. That makes sense? Anybody here a hunter? No? Well, then you are?
I have some.
Some? Well, you know what an over and under shotgun is then, don't you? And you know what a double barrel shotgun is, right? Well, there you go. There's your double barrel and there's your over and under. Okay? Kind of if you look at the wrong end of the shotgun. Okay, I don't know if y'all even understand what that means, but if you're not a hunter, you might not know. Or maybe if you're a enthusiast of Western movies or something. Or guns. That's true. Maybe military, although they don't use shotguns as much in the military. Most of the shotguns used in the military will be either over and under or neither one. It's a single barrel. So there's your Lewis formula. Because what we do with the Lewis formula is we replace only the shared pairs with lines. Only the shared pairs get replaced with lines. And then from the Lewis, from the Lewis dot formula is better, we can see I have 1, 2, 3, 4 pairs of electrons that are shared. Okay? From that, 4 pairs of electrons around that central atom, 3 of those are shared. It's from this that I get this shape. You can go from there, but I like to think of it this way. So our formalized system then we're going to start using for figuring out molecular shapes will work like this. I want to start with, how about oxygen dichloride, all right? Oxygen dichloride. So we're going to look at the periodic table, and we'll see that, I hope by now you can figure out how many electron dots there are around oxygen. Oxygen is going to have 6 electron dots. Okay, and chlorine is going to have 7 electron dots. Okay, so we start with the electron dot formula, then we go to a sharing arrangement, then we go to a Lewis formula, or Lewis dot formula really. We don't really have to go to the Lewis formula itself to get our three-dimensional shape. And we're going to count the number of the number of pairs of electrons, both shared and unshared, around whatever the central atom is, whatever the atom is that's going to define what the shape of this molecule is, okay? And I usually call it a central atom. Now, when you get to college, there are going to be more complex molecules that you have to be able to figure out shapes around more than one atom at a time. But for right now in high school chemistry, we're only trying to figure out the shape that exists around a single atom one at a time. Got it? So we care about the shape of the molecule, and we're going to define that with these simple molecules by what's happening with this central atom here. Got it? So now that I have the Lewis dot formula, I'm going to count the sets of electrons around the central atom. And if I have 4 sets, it's always going to create a tetrahedral shape. That's what we talked about yesterday. And a tetrahedral shape, since oxygen is our central atom here, you're going to have something going up, something going to one of the 2 sides, either this way or this way, like we said earlier. Doesn't matter if your double set's on the left side or the right side, or even above, as long as you have everything kind of arranged properly. Then you've got a set going behind and a set coming out toward you. Okay? So I'm going to take, and right now, I'm initially going to only put those electron dots that are around this central atom on these arms. Okay? So we start with the electron dot formula. We do a sharing arrangement. Then we get a Lewis dot formula. We count the sets of electrons around the central atom. We put as many arms as necessary to put that number of electrons around that central atom. And this shape is going to be called an electron dot shape. Okay, so it's a tetrahedral electron dot shape. You need to know that it's both geometry called tetrahedral, and the type of drawing, the way we arrange electrons, is electron dot shape. Okay. So this is 2-dimensional. It's not really the shape. This is more getting closer to the kind of shape for the molecule we're looking for. And we started out with this with what were called electron dot formulas. And then we made that into a sharing arrangement. Then we created a Lewis dot formula. And we've learned about Lewis formulas. We'll get back to those later, but we really don't need a Lewis formula to go to this. And then we get this electron dot shape. From the electron dot shape, then, we're going to draw another drawing that's exactly the same. I hope you're doing this in pencil because there's some erasure that's going to be involved in this, okay? So we're going to draw this exact same drawing here. I'll move it down here. That's the way people will expect to be able to see it. Well, I should say tetrahedral electron dot formula. It doesn't matter. Shape or formula is fine. Okay? Then what I'm going to do is I want to say, go back to my Lewis dot formula, and I'm going to count the shared sets of electrons. Now, I said sets and not pairs here, okay? That's important. It's the sets of electrons that define which shape we're going to have down here or here. So we're going to count the shared sets, and I'm going to replace that number of sets with the element they're shared with. I've got 2 shared sets. It does not matter on a tetrahedral where I put it. I can put the chlorines here or here, or here or here, or here or here. It doesn't matter. Okay? I'm going to take, in this case, just because it's what I want to do, I'm going to put them here and here. This is still tetrahedral. And this is called, I'm going to call this a modified electron dot shape or formula. Okay? And when you get to college, there are going to be some shapes you'll learn where it does matter where you put them. But for tetrahedrals, it doesn't matter. Okay? I'm trying to remember if it matters any time in here. I don't know if we're going to get that far with molecular shapes in here or not. All right, now, Then we got to have one more step here to find what's called the actual molecular shape. I want to redraw this exact same thing. And to get the molecular shape, we're going to erase the arms and the lone pairs that are on those arms. Okay? And this is how you can you find and define the molecular shape. Okay? This is no longer tetrahedral. Remember, tetrahedral had 4 arms equally spaced, right? And this is not a tetrahedral anymore. We have to have a new name for this. And it's a really highly technical name. Bent. Yeah, that's a joke. It's not technical at all. It is called bent. Okay? That's what it is. It's a bent molecular shape. Okay? So the shape of this molecule is bent. Got it? Some of the names seem kind of technical, but some aren't so technical. Got that? Does that seem hard? No? Okay. It shouldn't be. Let's do one more shape. I want to let you do it. Okay? Figure out the shape. How about nitrogen trifluoride? Nitrogen trifluoride. Nitrogen trifluoride NF3. Okay? All right, looks like everybody's doing a pretty good job. So let's move forward here. I'm going to show you how this works. So here's nitrogen, and there's 5 electron dots around it. Fluorine's going to have 7 electron dots. And then we're going to share the electrons. So we're starting out with the electron dot formulas. We're going to share the electrons we can to get both the nitrogen and the fluorine up to 8 valence electrons, or whatever number of electrons they need. In this case, it's 8. Go to the Lewis dot formula. Don't forget the lone pairs. Those have to be there. Can't leave them off. And then I can count and see that I have 1, 2, 3, 4 sets of electrons around that central atom. If I have 4 sets of electrons around that central atom, I need a tetrahedral shape. So I start with this shape. Whoop. I guess I'll darken that one in. And we're going to start by just putting the electron dots that you find around that nitrogen. The 1, 2, 3, 4 sets around the nitrogen. 1, 2, 3, 4 around this. Then from that, I'm going to replace, in this case, 3 of those sets. Now, I allowed you in this example to put your sets, your fluorine atoms anywhere you wanted to. I'm going to put them down here because it makes it easier to see the name of the shape we get out of this, okay? And so this is called the tetrahedral electron pair shape. This is a tetrahedral modified electron pair shape. And finally, the molecular shape will remove that pair of electrons up there. And I recommend, even though I've kind of skipped that step, that you draw that exact same drawing down here in pencil and erase that leg or that arm with the electron dots on it, okay? It'll keep you from making mistakes that are going to cost you big points on a test. All right, so don't skip any steps right now. Okay, these are your training wheels, so you can get to be really good at riding this bicycle, and then when we take the training wheels off, you'll be all set. Okay. Now this isn't called bent. This is a different kind of thing. Let's see. Let me draw out a little drawing here that kind of shows where we get this name from. See if you can help me figure out what it's called. I bet you can. What's that look like? Yeah, it's a 3-sided pyramid. Okay, so this is going to be called a trigonal, or 3-sided pyramidal shape. Okay? No, you don't have to, but it's easier to see the shape when you do. Okay? Any of the other shapes that I saw you guys doing were perfectly okay. All right? You could get rid of your lone pair. Could have been out on this arm right here, and you got rid of this, so you had two arms like this and then a dotted line. It's like you're almost looking almost down on top of it. It's still a trigonal pyramidal shape. It's just easier to see when you do that. Okay? If you're not good at picking it out, then make sure you put them down here. That'll help you. Got that? All right, so do what you need to do to get the right answer. Okay? All right, one last thing before we move on to the next thing I want to get to on these. Occasionally we get molecular shapes where we don't need three different three-dimensional drawings. Okay? Let me show you one of those. This is real simple. If I were doing methane, methane is CH4. So with methane, then I've got carbon, which has 4 electron dots, and 4 hydrogens, which have 1 electron dot, and hydrogen only needs 2 to have a full valence level. You need to remember that. So with the sharing arrangement, then this is the electron dot formula, or the electron dot formulas plural for each of these atoms. Share them like that. This is going to give carbon now 8 electrons, and hydrogen only needs 2 to have a full valence level. And so I get the Lewis dot formula. And then the three-dimensional shape, we'll start with the electron pair shape. That will be tetrahedral. And so when we go to the very next shape, we replace any sets of electrons that are shared with the symbol for that element. There will be no lone pairs, or there will be no arms with only electrons on them. So there's nothing to erase. There's no arm to get rid of here. So this is the final shape. All right. So this is one of those cases where you don't do three-dimensional drawings, only 2, and that only happens when you don't have any lone pairs. So this is a tetrahedral electron pair shape, and this is a tetrahedral molecular shape. Okay. What I want to do from this now is to move into something that's called double bonding. So far, the kind of bonds we've been showing are all single bonds. Okay? And just in terms of the terminology we're going to introduce here, single bonds are sigma bonds. All single bonds are sigma bonds. When we introduce double bonding, we're going to be introducing something called a pi bond. Double bonds have one single bond, sigma bond, and one pi bond. Yes, it's the same symbol you use in math. Okay? Sigma is like an O with a swish. Okay? And pi is, you know it from math. Right? Got that? All right. So let's see here. What would be a good one to do? We're going to do this molecule right here. Okay. You guys probably know that name from your other science classes. Biology, maybe? No? Formaldehyde? You never heard of that before? No? Well, you know when they had those biological specimens in those jars, that they're in a liquid, they're usually stored in formaldehyde. Now, it's kind of dangerous stuff, so they eliminate it a lot in high schools, and they'll replace it with ethanol a lot of times. But ethanol is not as good at preserving things as formaldehyde is. Formaldehyde will keep a biological specimen virtually forever. Okay, an alcohol like ethanol will not, it'll eventually break down anyway. But if you don't need it, but maybe 10 years, it's fine. Okay, all right. So let's see. Let's do our Lewis dots here. Hydrogen only needs 1 dot. Carbon needs 1, 2, 3, 4 dots. And oxygen needs 1, 2, 3, 4, 5, 6 dots. Okay. We do the sharing arrangement. I can share these 2 electrons here and these 2 here. And hydrogen only needs 2. Carbon needs 8. This carbon now has the 4 it started with plus 2 more it's sharing. This oxygen has 6. If I share these 2 electrons, that gives the carbon and the oxygen only 7 electrons. And the only way to put this together so that both the carbon and the oxygen have a full valence level of 8 electrons is if I share a second electron. And that's the double bond. Well, that's the beginning of it anyway. All right? So what we have here, if we were to do the electron orbital notation for oxygen and carbon here, we would see that there would be sharing or overlapping of 2 different orbitals between carbon and oxygen, okay, which is kind of hard to draw out on paper. But that's what happens. And whenever you share an electron covalently, you are combining 2 orbitals, right? They become the same orbital. All right. Let's see how this works out on paper then when we get to get these shapes. Let's do our Lewis dot formula first. Carbon is kind of the atom in the center, so I'll start with it first. And I've got a pair of electrons I'm sharing with this hydrogen, a pair of electrons I'm sharing with this hydrogen, but I'm going to share 4 electrons with that oxygen. And the way that you do that is like this. It's kind of like 4 corners of a box. Okay? The remaining 2 electrons on the oxygen just so you put out there somewhere. Okay, remember that we kind of think about it as being 4 sides of a box and put the electrons on the 4 sides. So these 4 electrons are shared between the carbon and the oxygen. Got that? All right. Now, a while ago when I said we want to draw shapes, the 3-dimensional shapes, starting with the sets of electrons. Well, these 4 electrons are a set. So in this case, carbon has 1, 2, 3 sets of electrons. And the way you can get 3 sets of electrons as far apart as possible is just to have 3 arms at 120 degrees apart. So this is not 109.5. This is 120 degrees. Okay? And it just is kind of like a triangle with a carbon in the center. An equilateral triangle, okay? Although it's technically not exactly equilateral, we can assume it to be here. So on one of these arms, I've got a pair of electrons. On another one, I've got a pair of electrons. But on the third arm, I've got 4 electrons. And that's a set. Okay? So this is not tetrahedral anymore. This is a triangle or trigonal shape. But it's flat. And so we're going to call it trigonal planar. a trigonal planar electron pair shape. Got that? All right. Now we have to take that shape and redraw it again. And we're going to replace the electron dots with the elements that, or the element symbols for the atoms that fit there. So where I've got single sets of electrons, those are replaced with the hydrogens. Where I've got that double set, that's replaced with the symbol for oxygen. Okay. So formaldehyde then has a trigonal planar molecular shape. So the double bond is a little bit different. Yesterday we were talking about what the single bonds look like. So all these bonds, we started with, remember, originally before any hybridization, carbon had 1, 2, 3 p orbitals and 1 s orbital, right? And we hybridized that so that this is actually reflecting that stretched out, pulled out to one side, combined orbital over here. And this is a combined orbital, this is a combined orbital, that's a combined orbital. You can't put two orbitals in the same place for the same reason we can't have two sets of electrons in the same place. That's when we have those orbitals in the first place. So since I have a bond here where I've got two pairs of electrons shared between carbon and oxygen, I have to have an orbital, I'm going to have a set of orbitals that become a bond that are not in the same place. Okay? And so what happens is this. Here's the carbon, and I'm going to kind of, for the moment anyway, ignore the hydrogens. Okay? We're just going to look at the carbon and the oxygen. All right? So we have a different kind of hybridization here. We have a p orbital that we don't hybridize. A p orbital we don't hybridize. Okay, so we have one unhybridized p orbital. Okay? That means we can only hybridize 3 orbitals, 1s and 2p's. So this hybridization is not going to be sp3, it's going to be sp2. All right? Now, a hybridized orbital actually ends up looking like a single balloon. Okay? So what's going to happen is we're going to have a hybridized orbital coming out like this. We're going to have 2 hybridized orbitals kind of one behind the other back here. We'll talk more about this with the balloon shapes on Monday. And the oxygen does the same thing. You got a p orbital that's unhybridized. You've got a hybridized orbital coming this way. And the 2 lone pairs over here on the oxygen, those lone pairs are the hybridized orbitals that are going to sit back here like this. And the orbitals that are going to overlap and become one combined orbital, well, this is one of them. That's going to form a single bond. Or, I'm sorry, a sigma bond. Okay? The other orbital can't be in that same space. And that's why we have a p orbital that's not hybridized. Because this p orbital is going to stretch across the top. Remember, the p orbital is in 2 parts. The 2 balloons here make up a single p orbital. And it's going to do like that. And you can kind of think about it like a hot dog. Okay? This is the wiener, and that's going to form the bun, because the bun's in 2 parts. So just like the p orbitals are in 2 parts, the pi bond, that's what this is going to make, is in 2 parts. So the pi bond is going to be here, and it's going to be down here. That's in 2 parts. So the actual shape of this orbital doesn't look anything at all like this Lewis dot formula or this. Okay, the shape of this bond is a little bit more complex. We need to know what it is and why it is. All right, we'll spend some more time on that on Monday. Okay, for right now we just want to practice finding molecular shapes, you want to remember to bring your balloons on Monday. And if you're going, wait a minute, don't put everything away yet. Hold on. And if you're going to redo the, you're going to do the test makeup, you need to make sure you get all of your makeup questions done by Monday, so you can come and get help with anything you need. All right, on Monday. All right. So here's our homework problem.